Welcome back to differential equations. In this video, we're going to go through a review of the derivative. You should remember from calculus that a differential equation is an equation that relates a function to one or more of its derivatives. And so it's very important that we understand what a derivative is in order to do anything with differential equations. So let me get my head out of the way and let's start at the beginning. For some function y of t, you're probably most accustomed to functions as being f of x or maybe y of x, and we will be using functions in that form in this course. But it turns out that very often, not always, but very often, the derivative is most useful thinking about a derivative with respect to time. And so setting up our functions as functions of t and thinking about time as we go through is going to make applications a little bit easier. But for some function y of t, the derivative, which sometimes you'll see written as d over dt on y of t, and sometimes you'll see written as y prime of t, is defined using a limit. There are a couple of different limit definitions. The one that is most common is the limit as delta t goes to 0 of y of t plus delta t minus y of t all over delta t. And yeah, sure, you should be familiar with that idea of the derivative. It should be something that you have seen in the past. But we spent in calculus nearly an entire semester just trying to make sense of that definition. And what I hope most of you came to the realization of is that that's actually not a very good definition to work with. It doesn't make a lot of sense. So instead, I want to think about the derivative graphically, which is generally a lot more intuitive. So if I have a curve here, right, this is y of t graphed. So any one point is the point that has coordinates t and y of t. And I move from that point some distance, delta t, that will take me to a new point on the graph, which I'm going to mark in red. And this will be the point t plus delta t, y of t plus delta t. And if we try to draw a line through these 2 points, the slope of that line, remember the slope of a line is the rate of change of the function, is defined as the derivative, well, without the limit. The limit adds to this by taking this point and trying to slide it along the curve as close as you can possibly get to the original point. And that's how you end up with the slope of the tangent line, the line that is just touching the curve at that one point, because the 2 points you go through slide so close together that they are practically the same. And that's what the limit tells us to do. But the important thing here is I want to think about that slope as a rate of change. That's how differential equations are formed. That's how we work with them. A differential equation is an equation where you can compare the rate of change of some quantity, of some function, to the original value of that quantity or function. And the more there is, the more it changes, or maybe the less there is, the more it changes, depending on the particulars of the situation. But that's what we're trying to build here. That's the idea of differential equations. When it comes to derivatives, there are a few differentiation rules that you should be very familiar with already. In calculus, you get a lot of mileage out of the power rule, which says that the derivative of something raised to a constant power n is n times that same thing raised to the n minus 1 power. We also have derivatives for many other functions. You should know the derivatives of sine, cosine, tangent, cotangent, secant, and cosecant, although I can't honestly say the last time I needed cotangent or cosecant in a problem. Let's just quickly go through. The derivative of sine is cosine. The derivative of cosine is the negative of sine. The derivative of tangent is the secant squared, and the derivative of secant is secant times tangent. You should also be familiar with the rules of differentiation for exponential and logarithmic functions. The derivative of an exponential is just that exponential. That fact is incredibly useful in differential equations. Knowing that there are some functions who don't change when you take their derivative makes a lot of solving differential equations fairly straightforward. And then, of course, the inverse of the exponential is the logarithm, and the logarithm has a weird derivative. The derivative of the natural log is 1 over the thing you're taking the natural log of. All right, so those are the elementary rules of derivatives that you should be familiar with. You should also be familiar with 3 rules for combining them. The chain rule, if you have some f evaluated at u of t, well, you take the derivative of f and you still evaluate it at u of t, and then you multiply by u prime of t. The product rule, which says that if you have the derivative of the product of 2 functions, u of t times v of t, you get the derivative of the first times the second plus the first times the derivative of the second. And then we have the quotient rule for dealing with division. The derivative of u of t over v of t is similar to the product rule. Derivative of the first times the second. Instead of adding, we subtract the first times the derivative of the second. And then we're going to divide by that denominator squared. I don't feel that I need to spend too much time going through examples of how to use these rules. These are things that you should be familiar with from previous courses. It's probably worth taking some time to practice on your own. But instead of dwelling on that aspect, I want to go on and look at an application. Because now that we're moving into this idea of differential equations, we really want to focus on modeling aspects. How do we set up a differential equation? How do we realize that something can be described using differential equations? There are a couple of times where that can come up, a couple of different reasons why that can come up, but it mostly comes down to thinking about a derivative as a rate of change. And one type of application that you've solved previously is the idea of related rates. Come on, there we go. So here we go. A spherical weather balloon is being inflated by an air pump that pushes 1.5 cubic feet per minute of air into the balloon. At the moment where the radius of the balloon is 1.75 feet, at what rate is the radius increasing? The first thing we should recognize on this problem is probably that it is making a lot of assumptions about the physics of a balloon that are probably not fair. First of all, if a balloon is intended to be a sphere when it is fully inflated, chances are very good that during the process of inflating it, it rarely makes a perfect sphere. We're going to ignore that and just pretend that it's a perfect sphere the whole time because it's going to make the math, well, frankly, go from impossible to possible, not just easier, from impossible to possible. So an assumption that lets us solve the problem is often a good assumption to make if it's anywhere close to the truth. The next thing we want to look at is the fact that I am claiming that the air pump is pushing a constant 1.5 cubic feet per minute into the balloon. If you have ever worked with an air compressor before, you know, or you should know, that that's not actually how things work. An air compressor works by forcing air to have a certain concentration, a certain compression, a certain amount of pressure. And if that amount of pressure is greater than the amount of pressure in the container you're pumping air into, then air moves in. And the difference in pressure between these two locations changes the airflow. As you inflate a balloon, it takes more work to push the same amount of air in, or more practically, less air actually flows in with the constant amount of work that your air compressor is putting out. We're going to ignore that because it makes the problem go from solvable to unsolvable, and we want a solvable problem. Right? Physics is really good at ignoring frustrating details that make the problem too difficult. And differential equations is as close to physics as mathematics gets, so we borrow some of their ideas. Right. But with those caveats in mind, hopefully visualizing this problem is fairly straightforward. You can think about a sphere which is getting larger and larger and larger. And as the sphere gets larger, it takes more volume, right? The volume of the sphere is going to increase more by a slighter and slighter change in the radius. So the rate at which the radius is growing should slow down as more air goes in just from the geometry of a sphere. And that's what we're looking at. So if I get my head back out of the way, let's see if we can set something up. And so we know that we are talking about a sphere. We're talking about the volume of the sphere. So let's start off with that formula. V equals 4/3 times pi times r cubed. And we know that the radius we care about is 1.75 feet. We could use that radius to calculate the volume at the time we care, but that's not really what we're looking for here. Instead, we're looking for the rate of change of the volume, which we'll denote as V prime. Technically speaking, we should be thinking about R as a function of t. We should also be thinking about V as a function of t, because as time evolves, these two things are going to change. But we're also feeling very lazy, and writing of t on everything is just a lot of work, and we'd rather not, so we're not gonna. We have here R, we have here V prime. We have an equation that relates R and V. What we would like is an equation that relates R and V prime and the thing we are looking for, which is R prime. And we can get that by differentiating both sides of this formula. So we'll take the derivative of V, and we'll take the derivative of 4/3 times pi. Well, the derivative of r cubed is going to be 3. Sorry, I'm getting ahead of myself. Right? The derivative of V is just V. The derivative of the constant 4/3 pi is just 4/3 pi. Now, the derivative of r cubed, using the power rule, that's going to be 3 times r squared. But this is r, and we're taking the derivative with respect to t. R is a function of t, and so when we're taking the derivative of an r, we have to use the chain rule and multiply it by r prime there. Notice that the 3's cancel out here to clean things up a little bit, and we get that v prime is equal to 4 pi r squared r prime. We know what r is, we know what v is, we can calculate r prime. All right, so 1.5 is equal to 4 times pi times 1.75 squared times r prime, which means that r prime itself is 1.5 over 4 times pi times 1.75 squared. And if you want to leave it at that, you're welcome to do so. If you have a calculator on hand, that might be useful to use at this point. Let's see. I get that r prime is approximately 0.03 8976. I'll round that up to 390. And let's think about units. My times have been in minutes, my distances have been in feet, my volumes have been in cubic feet. And so this is the derivative of r, dividing the radius r, a distance, by time, minutes. So this should be in units of feet per minute. We can reason that out just thinking about what this thing means. If you're interested in that side of things, you can go back to that formula and start plugging things in. The measurement of 1.5 was in cubic feet per minute. 4 and pi are both unitless. 1.75 was in feet. So we have cubic feet per minute divided by feet squared. Cubic feet divided by feet squared leaves you with just 1 feet left. And so the units check out. We do, in fact, get the feet per minute we came up with here. Water is pouring into a cylindrical tank at a rate of 1.0 gallons per minute. Water is pouring into a cylindrical tank at a rate of 1.0 gallons per minute. If the tank has a radius of 3.0 feet, how fast is the water level rising? And after I wrote this down, I realized that that wasn't actually supposed to have been gallons. My problem in my notes goes through the whole thing pretending that that said 1.0 cubic feet. Right? 1 gallon is not 1 cubic foot. Those are not the same measurement. That was just a mistake in my notes. But yeah, let's go with that. Water is pouring into a cylindrical tank at a rate of 1.0 cubic feet per minute. And we will say the tank has a radius of 3.0 feet. And I would like you to calculate how fast the water level of this tank is rising. There's one implicit assumption in this that I think is fairly straightforward and obvious, but it is something that is worth pointing out. The setup of this problem has made the assumption that the cylinder is sitting in this direction with the water level somewhere there, and we've got water flowing in, which is causing the water level to rise. With how it's written, there is no reason that you couldn't interpret. That's behind me, so let me get my head out of the way. There's no reason you couldn't interpret that this problem was talking about a tank that looks like this, but it turns out that there's not enough information to solve that problem, so we don't want to do that. But I would like you to take a couple of minutes and think about how to solve this problem. Look at that last one we did for inspiration. Take a few minutes, try to work out your solution, and I'll see you in the next video.